¿Empezamos ya, Sergio? Vale. ¿Me hace falta el micrófono? Pues nuestro, no sé cómo se dice en castellano, el invitado que va a dar la charla. Sí, bueno, sí, pero prefiero que lo presentemos en español. Domenico Bonaccini Calia va a dar la charla hoy. Él lleva 20 años en la ESO y es el responsable de todo el tema de todas las actividades con láseres. Y la charla que va a dar hoy va a centrarse en Research and Development en sistemas LGS Systems.
Sí, ya está. Preséntese. Bueno, como primero, muchas gracias. Es un honor de ser aquí con ustedes. Y por favor, me interrumpe o me habla cuando quieres. No tengo problema. Y ahora voy a switch in English. No puedo justo hacer la charla en español. So the topic is laser guide star research and development, laser guide star adaptive optics technologies research and development. It's a work package at ESO. You will see, but it's not an activity of ESO. It's actually it's an activity which is clearer and clearer that it has the buzzword synergies. I wrote it in Spanish because I wasn't sure in English if I could spell it properly. Then I found out afterwards. So you see here some names and institutes. At the moment, we have the ESO people of the Laser Guide Star group, myself and other people you can list here. Some of them have come to the observatory already and have observed. Some more will come later. Then there is the people from the Observatory of Rome, Osservatorio Astronomico di Roma. They have also contributed to a good part of the system. And then there is this institute people and the Grand Tecan people, which are collaborating to the experiment. And you will see that later on we will have more of these collaborations. So I'm only trying to coordinate. So what I'm presenting is the work of a lot of people. It's not my work only, and actually everybody is bringing their brain into this. So as I said, it's a work package in our technology development program. I have the honor to be the work package responsible for this, and we have some strategic thing to do because we have big projects. So both expansion of the VLT laser guide star adaptive optics. You have the Grand Tecan laser guide star adaptive optics coming on. Other telescope in the world, big telescope also are progressing in the systematic use of laser guide star adaptive optics, but the technology is not completely matured yet. And so we have this activity going on. And I will focus here on the field tests that we did with you. I wanted to present you that we're achieving good results, actually, thanks to this collaboration, and also what we would like to do. We are using this transportable laser guide star unit called Wendelstein laser guide star unit. Wendelstein is a mountain on the south of Bavaria, where we were supposed to do the first light. Then we didn't go there to do the first light, but the name remained attached to the system. So the other thing is that, as I said, we have a number of institutes which are participating, and there are new institutes which want to participate, and that's what I wanted to show you, to future experiments. I know this is not the first one. So, in the summary of this talk, first we have, and we are doing still, the return flux experiment at the Observatorio Teide, and I will show you some preliminary results. There is another observing run starting on the 4th, so tomorrow night, and there will be 2 more runs next year. Then I want to explain or present the test that we will do next year. In the summer of next year, near the WHT, we have foreseen, and it is approved to do another test. And I just put 1 year span because we have to reduce the data and maybe I hope we don't have to repeat tests, but normally my experience is when you do field tests, you do the first field test, you have to redo it a couple of times before you believe what you're finding. And then there is a proposal that I wanted to just introduce to you for the other years to have some more joint experiment to see if we can push the laser guide star adaptive optics toward the visible. So to have correction for the visible on telescopes of 8, 10 meter. So the size you are also, I think, interested. And could be also useful for the E-ELT to increase the Strehl of infrared adaptive optics with laser guide stars. So these are ideas which are circulating in our community, but there is no place to test these things, okay, so far. So here I am, I'm going on the, I think I've jumped it a little bit. Yes, okay, something is happening to this. So here you see simply the laser guide star, the laser of the laser guide star unit, which was a development which was completed in 2010 actually. And it allows you to have a continuous wave laser and also some amplitude modulation pulse mode. It is a very good beam quality, and the important thing is that the same technology that you now can have from a company called Toptica. So ESO decided to transfer the know-how so that this is produced in an sound engineering robust system. And I can tell you we have installed one now on the VLT and commissioned it. And we are going to install 3 more and commission them in the next quarter, so first quarter 2016. There's a team of people. We have already shipped everything. We just passed the so-called preliminary acceptance Europe. So it's a set of tests with a certain external board which has to decide if we have compliant to ship things or not. Okay, and we just passed it. You can see an announcement in the ESO web pages. So, but this laser is basically the first prototype of this technology that was really tested in the field, and it has been tested also now here. So, if you come and see this laser in the sky at OT in the next nights, you can imagine this is a fiber laser. So, do you see well this image? Yes, it's based on a Raman fiber amplifier, which was developed, and there's a seed, and then there is an amplification of this wavelength to 1178 nanometer, and then is a frequency doubling later on. You see in the scheme here that we go with this infrared power into a nonlinear crystal, which converts 2 photons into 1 photon 589, and there is a control system for it. I don't go much into the technology of this, but basically the element of novelty was the narrowband Raman fiber amplifier at very high power, and then all the rest were parts that we could put together and then get it industrialized. This is the only important thing was the size of this picture. The size, you will see later, is quite small. So the laser head is only 50 centimeter by 35 by 100, and so it can be attached to a telescope directly. And this changes completely the problem that many observatories have, how to relay the light to the launch telescope. Sometimes the launch telescope is behind the secondary mirror, sometimes on the side, but you still have, if you have a clean room with a big laser and then you have to bring the light there, you have to invent very crazy systems to maintain. So these lasers can be attached directly. This is one of the things that we wanted to develop. So in fact, it is attached to a launch telescope. Here you see the drawing of the design. So the launch telescope is quite simple. Is a Galilean projector with a focusing element here, so we can change focus. It's a carbon fiber structure, and I try to go fast. The other thing is that we have implemented it here together with the receiver. So there is some architecture. There are two industrial PC computer, and it's all controlled with LabVIEW. Okay, so this is really an experimental system, but it's working quite well. It has a photometry receiver, 40 centimeter with a CCD camera and Johnson filters, which is pointing in the same place, and we can implement sort of automatic observation. This is just to give you the scale. Okay, this is in Garching, and we mounted on a robust tripod This entire thing is about 90 kilograms. And the laser head is about 35 kilograms. So the questions we are doing in the first experiment, which is running right now, and for which you will see some of the answers, which are quite nice, is how much return we get when you point in different directions. It's quite complicated how the sodium atom interacts with the laser radiation. It's complicated in terms of how much return you can get because there are different things which play. The laser format, circular polarization, linear polarization, the spectral properties of the light emitted, the concentration of the light emitted, and of course the frequency, and also the direction of the geomagnetic field. So the geomagnetic field plays a big role actually into the optical pumping of the sodium atom. So basically it reduces the return flux if you point in directions which are orthogonal to the geomagnetic field. And the question we want to know is the laser we have deployed in Paranal has a fixed format. So a fixed choice of polarization, fixed choice of spectral format, fixed choice of power. Do we need to have a laser in the future which is varying some of its parameters? So when we point in this direction, it's better to have this format. When we point in that direction, this is the question that we wanted to answer. And we wanted some statistical sample. Because if you do just a measurement, you have a certain sodium abundance, a certain seeing, so you have a certain spot size of the mesosphere, and so this can change. And it does change. And not only we want to see what we get, we would like also to improve our models. I'm not the most expert of the models. One of our team is one of the people which are expert in models of the sodium atom interaction with the laser light, but we want to anchor these models to the reality, so we want to verify or change the parameters of the model. So what are we changing in the laser? We are changing these parameters. So we're changing line width. Maybe I can use the mouse. Let me see. Do you see the mouse? Yes? Okay. So then I can stay here without turning back and forth. We can change the line width of the laser, so the emission line width, and it's given for lasers in megahertz. These are fraction of a picometers, okay? So we can change the polarization state of the radiation, the emission in the D2B line, so we emit a fraction of the light in a secondary line of the sodium for a good reason, and the power, of course, and the frequency of the repumper line we can change a bit. What we have implemented here is this 350 millimeter diameter projector with certain pointing error. These are all numbers we have derived from the commissioning. And this is where it is. You have been there maybe, but this is the dome that the ARC has prepared and we have really used together. At night we have to go back and forth sometimes in this dome from the Mons control area. And we have implemented this receiver telescope in a secondary dome. And you can see just two pictures. The left picture is the launch telescope with a laser head attached on the bottom, this yellow that I'm indicating now, on a pier, on a steel pier, and then the receiver telescope with the CCD camera attached. These beautiful pictures are from Daniel Lopez, and really he's done wonderful pictures, but I just wanted to show you the schedule we're following. We started in December 2014 with the installation, and then we went on into the commissioning in January, and then we started observing in February. And what we're going now is this run of December that you see in bright yellow. And then we'll have, this is not going to be March, it's going to be April because of the activity in Chile. So when I have the head of activity for the 4 laser guide star project in Chile, I have to go there, so I cannot be here. But in April we will do, another run. And then there is, in May, when we dismount everything, actually, we will do like 2 or 3 nights, and then we will dismount everything and remove it, and we will go to, you will see later, to WHT or close to WHT in La Palma. We have implemented, thanks to the people in Rome, the observing system in a very automatic way, so at night we don't make confusion because you're tired. And you make the system is quite elaborated. It has a laser changing parameter, it has a CCD camera, it has rotators, focusers, trackers, so we have to be careful. We have reproduced the scheme of the observing blocks. So we produce an ASCII file before the run, and ECR and Marcos knows very well what I'm talking about. And then we have a list of stars we want to point, and then we start clocking, basically. So taking data and storing data. But we have a real-time, sort of real-time display. Every time an image is ready, there is a program in the background. This is IDL program. It's also been done by the people in Rome. I have only participated into, my glasses are breaking, into the definition of this. And the program gives us what we are seeing. What you see here, you see the laser guide star here, a natural star nearby, of which we know the magnitude for the photometry. Here you see the profile of intensity, of relative intensity along the laser beam. This is, of course, convolved with a pixel scale, which is also varying. The projection of the pixel scale is varying in altitude. And we also monitor, at a height of about 40 kilometers, we monitor the return from the last Rayleigh scattering, because this tells us a bit of the transparency of the atmosphere, if there are cirrus or also if there is a variation, so we can normalize the results afterwards. This is running, and then it's producing basically a set of data in ASCII files that we can elaborate afterwards. What we've done so far. So far we have sampled, you can see this polar plot, you can see the zenith is in the center, and then of course there's the down to 30 degree toward the horizon. We have sample stars that you can see different runs. So in February is in blue, in June is in red, and September is in green. So we do about a week run every quarter. Now this is, we do power scans with different configurations to try to determine the sodium content. We use our models, of course, so we have to trust at the moment our models, because we don't have a way to measure the sodium content. But our model fit pretty well the data, so it's quite important. We have 4 different measurements with different sets, and by this we fit 2 things: the spot size of the mesosphere and the sodium abundance. And then we see the sodium abundance here. In this work has been done by Ron Holzlohner, which is one of our team members, which is dealing with the modeling. And this is what I told you before. You can see here a polar plot at here at OT, and the numbers you see is these numbers represent the return of how many photons you get on the ground per square meter per second in millions. So you get 14.7, you predict 14.7, 15 million in the best spot, which is this red one. The optimal spot will be here, where the magnetic field line are parallel to your laser beam. Okay, it's quite close to 30 degree. But of course, the transparency of the atmosphere actually favor this area, because you have more return, but you have less transparency because you're a big air mass. So, but basically, we are trying to check that this is what we expect. This is a plot for a particular configuration, a particular sodium abundance, and so on. But it's a modeling. So I'm going to show you some more results. But there is a big number here. It's called SCE 330 equal 330. So to tell you what we have in Paranal with the old laser that we used before, the linear laser we used before, was something around, this parameter tell you how many photons you're getting per atom, let's say, from your configuration, average across the beam. And basically, we had with the old lasers something like 60. With the Air Force, with their laser, had something like 120. Okay, and so you can see that we are getting, with choosing the parameters properly, we are getting more. And what it means you're getting more, it means every watt you emit, you get more flux. So basically, you have, given the cost of the laser power, you have quite an advantage. Sorry, this is a fitting of the D2B frequency. These are all results obtained here. On the left side, you see a plot where there is the power density at the mesosphere in watt per square meter. And on the right, on the vertical axis, you have the deviation in frequency of your repumper D2B line, the secondary line that you are emitting. And basically, you can see from this plot that if you try to fit this plot, will give you a maximum, the right plot gives you a maximum return for a certain frequency. It is exactly this frequency. So what we model seems to be correct. And also, if you try to fit the slope of this plot, you should be around here, which is also what we expect. This was a good seeing night. I must say we had incredibly good seeing in September. This is another thing we tested. It is it is how much the return flux vary if you change the line width of the laser. There are different plots on the left side. These are all theoretical plots. What you see for Mauna Kea is it's almost identical of the Canary Islands. It's really almost identical. And so this green dashed curve represents the SE that you would get. And this, what we haven't fitted yet anything, but this is what we get. So we get a similar slope, essentially, when we measure here. This is also reassuring. This is a different result. I'm trying to run, and you stop me, because I'm trying to go because there are a lot of slides. This is instead a scan of the intensity of the secondary line. So we have an emission at the D2A line, 589 nanometer, and the D2B line, which is 1.7 gigahertz toward blue. And basically, we are increasing the distribution of these two lines to see where is the optimum, okay? And so you have, in the horizontal axis, the percent of light emitted in the D2B line and the flux here. And you can see that there is, in this case, depending where you point, this is one thing we discover here, which we didn't know. Depending where you point, your optimal is different. So depending on the direction of the magnetic field compared to your direction. And this could be one thing, we have to finish the data collection and then the analysis, but this actually could be one thing that you will want to change. This is about a 10% change. Right now we normally operate, for example, with optical laser, we operate around 10%. And you can see in this case, difference between the 10% and the higher percentage, it's more than 10% in flux. So you would like to have a laser that you can adjust a bit this. This is another set of results we have done with a polar map of return. These are ratios of return with the best configuration of the laser and the worst configuration of the laser. So you can see that in the best cases we have an improvement of 240% compared to the traditional lasers, okay? I'm trying to show you quickly the data. So this is showing you the return flux in the best configuration, which we had in June and in September. So there is the sodium is getting more abundant when you go toward the cold season. This is basically the rule of thumb. So in September, we have more return than June. And it is true. But the important thing is the numbers. You can see that these numbers are quite high. If we compare this to what we got in Paranal, because we did a campaign in May and in August, they're comparable numbers, by the way. So they are, the results we find here are not too much different from what we see in Paranal. Basically, we got in Paranal return flux between 8.5 million and 26 million photons per square meter per second. Now, everybody in adaptive optics will love you if you give him these numbers, because our specification in Paranal is 7 million, and it's in it for a certain sodium abundance, and we meet this specification. Seems that we are meeting this specification, and actually we have a bit more margin. And also here we find similar things. We have fluxes. You can see this color plot. We have fluxes between 27 million and 8.5 million in the campaigns of June and September here. Well, no. In fact, only the sodium abundance should change, and also, of course, if you have the direction of the geomagnetic field, you could have different areas where you have better return. So if you have for example, imagine if you have your geomagnetic field directed to zenith or close to zenith, like it is the case in some observatories, then you have a very high peak return here, very, very low at the horizon. And we have a similar distribution also in Paranal. Our geomagnetic field best direction is very low, it's 21 degree, although it's in a different direction. But so basically, people could say, well, but you don't know exactly what you get in the other place, right? You're measuring here. So I want to say that this is showing that actually, as you say, it's predictable that should be similar. So this is the summary now. We have a transportable system. We install it here with you, and we have worked together also with your people and other people to use it. And I think we have a plan to use it until May. We are doing these missions every quarter, so you will see me around every quarter. But we are trying to compile a good database. Now, what has come out from this work is that it is very useful for the modeling, to compare with the model, to have also the sodium profiles. So in the mesosphere, the sodium is distributed, the abundance is not constant, it's distributed, and it changes also with time. And so we had the luck that Julio could work with the EIC-80, and this morning you showed the first hot results. And so I hope that we can get this, because it's quite useful. We will plug your results when we have sorted out the wires, when we believe them, when you believe them, into the simulations and see what we get. But I think it's very precious. It would be nice to have also the sodium abundance, so to calibrate this for sodium, but we are not there yet, I think. So we have to use our model to derive the sodium abundance, so we don't have a direct method to measure. But it's very good. It's coming in place, and I want really, we are very thrilled that we could do this with you, because, it's the first time that people can dedicate time to do these things. And normally people get this, the observatory which got the laser, they just put it on and try to observe and put into a program, so you have no time to really do a campaign and discuss and understand what to do for the next generations. So the other thing is that it's true that circular polarization with the repumping, so with a certain percentage in the other line, gives always the brightest LGS. This was predicted, but this has been demonstrated. We can use the model to find the sodium abundance, seems to also to work. We have measured high values of our SCE, so it means the atoms are used efficiently. They are really absorbing photons and re-emitting in preferential directions using a particular type of setting in the laser emission. So I hope, Julio, you can come and do more profile in this campaign, then we can use them. Yes. So now I speak about next year summer. So in May we transfer everything, hopefully in one day, just the transport one day, to WHT, and then we remount everything there, and we are building a special container for the laser operation next to the WHT, if we get the permission from the authorities, Marcos. But as you see here, there's more partners, because there is the Canary Laser Guy Star system, which is a system built exactly to do experiments with the WHT, and is also running, not only for experiments, but it can be used very well for experiments. So there's new players. There's the Durham University team, very strong team for adaptive optics, and also an equivalent strong team from the Observatoire de Paris. And then us, and of course the people of the ING, which are running the observatories there. And this is quite a unique setup. I say here what everybody is doing, and I think the AIC could also, if besides working with us on the laser, could also work with the profiling. This will be very good. You will see in a second that, because in this picture, what we want to do, we want to, sorry, the cartoon is very poor, but we want to project the laser beam to the mesosphere and observe it with the WHT, which has the Canary system and the wavefront sensor for Laser Guy Star. And we want to use a natural star, and at the same time, on top of it, to measure the wavefront with the laser and with the natural star, and see how the two compare. Now, what are we doing? We're putting the laser about a 40 meter from the edge of the WHT. So this will be the E-ELT configuration. The E-ELT will project from the side. And so on the other side, the subapertures on the other side, we'll see very elongated spot. I mean, we're talking 20 to 30 arcsecond elongated spot. Huh? So real cigars. And you can see here a picture of what the wavefront sensor will look. And nobody has observed in this configuration. There have been experiments in the lab, but nobody has really put all the real life things into this. This will be the first experiment, and we can do this only because there's people which have, I like this picture all the time, there's neurons which know different things. And by putting all these neurons together, so our brains together, we can do more. We can really achieve this. It will be very difficult, if not impossible, for a single institute to do this, because of the hardware, because of the software, because of the know-how. And this is really, I just coming back from a meeting where we had a sort of coordination, what to do next year, who is doing what are they preparing, what are we preparing, and this was quite enriching to see. There were a lot of people, a lot of PhD students, and really nice atmosphere in Durham. We did this meeting. So what I wanted to say is that there is the proposal, or actually accept the proposal to use the INT, so the 2-meter telescope, which is 400 meters away. So I think it's about what IAC 80 is from now. What are you now? 4 times more, okay. Okay, so. But anyway, in real time, so they will have a fast camera, very sensitive camera. In real time, they're going to take the profile and feed these profiles to the adaptive optics. Because what is the adaptive optics doing? They are experimenting which filter, how to calculate the centroids in the Shak-Hartmann wavefront sensor in the direction of the elongation, which is quite difficult task because it's moving very little compared to the length. And there are different schemes proposed, but nobody again has really tested them. And knowing the profile it's an important thing. And so I hope, Julio, you'll have the time to give your help to this experiment. I don't know, but the people in Durham are building actually this profiler, and we have planned to test it for 2 nights when we install everything without the WHT. We will ask only if we can test the profiler, just that you know. So this will be very end of May or maybe very beginning of June. Should be there. So here you see a picture of the E-ELT 40-meter aperture and the WHT projected on it. So you can see to give you the size, a 4.2-meter telescope looks very, very small compared to the 40-meter telescope. But this experiment is really for risk reduction for the ELT. We felt this. We started discussing this in 2012. We felt it was really difficult to go in the sky and not having an evaluation, a real evaluation. So I'm very happy that we can do this together. So now I come to almost to the end. The first thing is what I said before. There's a wonderful. We get wonderful results. Oh, this is cut. Oh, it's cut on the display. I'm sorry. We have wonderful results by putting together the Lego pieces or the equipment the different institutes have, and the know-how the different institutes have, and also the enthusiasm the different institutes have, because by doing this, we really can achieve much more. And this is what we have done here so far is the first attempt. So what will happen later, I hope it will happen, is that more institutes join to do a new type of experiment, and we get some answers. We have so far achieved good results with the return flux experiment, and we are trying to start the matching of the model. So far, also successful. We will finish in May 2016. Then at WHT next year, so second quarter, third quarter, maybe you'll go a bit also into the fourth quarter, we will do this LGS-AO field tests, and we will see how much we can get. So we have asked for some nights, and we hope we get some nights this time. But then, this is the last point. We still have many questions unanswered, and I put some here. Will the phasing of segmented primaries be possible with laser guide stars? If you don't demonstrate, no matter what the theory says, people who build things don't believe it, okay? And so this is one question. Will the use of this wonderful pyramid wavefront sensor, I don't know now if you know what is the pyramid wavefront sensor, there's a little scheme down here, but it's a sort of new thing in adaptive optics, is giving very nice results where it has been installed with natural stars. Operation with laser guide star has not been demonstrated, and it's not even in the lab demonstrated. So this is a new thing which is coming up, because why that? Because it brings you the possibility to use adaptive optics with laser guide star in the visible. So far we are using it in the infrared because there are some limitations. And can you obtain then, even still with this wavefront sensor, even higher Strehl ratio for the E-ELT? Some instrument, second generation instrument in the E-ELT want to have a high Strehl. So want to detect planets and things like this. So we need to find a way, we have time, but we need to find a way now to, I mean, in the next years. So I'm talking about what is needed in our community. So I'm asking, who can do feasibility of this new concept and push the technology? Who can do this? And I think we can only do this if we join. Not even in the US, there is a single institute who can do this complete set of tests. So we have a sort of unique situation in Europe, because we have some very good groups in Italy, in France, in England, in Spain. We have ESO, which can coordinate a bit of effort. We can really do, and you in particular here have these observatories, which are quite nice and close to everyone, and we can really try to use the best for this. Plus we have projects. You have projects, other institutes have their projects, and they're all going in this direction. So we need to perfect this this technology. So my question is a bit to formulate. I already spoke with other people in the other member states, but it has to be approved, it has to be proposed, it has to be concrete, and this will come middle of next year, I think. But the question is, can we use the WHT and the Canary system, which is really perfect for answering these questions in future years? I think we need 2 weeks per year of observing time to test the various things, but because it takes time to prepare and takes time to observe and to reduce the data. So if we have maybe 2 or 3 runs of 5 nights distributed across, it will be enough. But it has to be a sort of an agreement, and this has to be put together. And of course, the funding is another issue, how we get to funding. But but it's funding and people, and we have to decide if we want to answer these questions. I put now down just the players that could participate, which can everybody bring something different, something new, something, and maybe even more later on, because when you start entering into these things, you have more ideas. But how to improve things. But I put the IAC, ESO, Durham University, Observatorio de Paris, the Observatorio Astronomico di Roma, Arcetri in Florence, they are the world expert for pyramid sensors, and the Max Planck Institute for Extraterrestrial Physics, which is our neighbor in Garching, which also have very strong know-how and adaptive optics, and in particular this experiment that I was trying to portray. And so I thank you with this. Sorry.
Thank you so much, Dr. Bonaccini, for this talk. Now we have time for questions, in case you have. Yes.
Hi, Domenico. Could you say a few words about the use of laser guide star in daytime for sun and the experiment that we have been talking about?
Yes, yes. So we'll try to start this time to do an experiment together with a vacuum tower telescope to see if in daytime we can detect and use actually later the laser guide star. What is the use for it? Okay, it's solar physics will love it especially to look near the corona with corrected adaptive optics, but also the thermal infrared astronomy will love it, because you know that you can use in daytime the telescopes if you go beyond 3.5 microns, and so you open another period of observations almost without competition for people who use the thermal infrared. And they can do adaptive optics. They could do adaptive optics with laser guide stars. And now we can speak, for those of you who know, we can speak about the tip tilt problem, but let's not speak it now. But we want to do this feasibility experiment. This is another sort of side outcome of being here, because you need a narrowband filter, and the solar people have narrowband filters, and so we are basically trying to demonstrate an idea of Jacques Becker's. He did the first calculation and the second calculation about this, and it should be possible to see it, and we're trying to demonstrate that we see it. Some people, I think some geophysicists have used it in daytime, but we want to see it, how much we see, and we don't have a pulse laser. We want to have a laser of the type that we will use, because they have different type of lasers and different requirements. So basically, we wanted to try these experiments together with you, Luis, and other people from the VTT in the coming days. And I know that I guess you are interested for the satellite communication. You should know that I'm also in touch with Ramon at the DLR in Germany, and they also expressed your same opinion, that they will be very interested to see if it can be used.
I have a suggestion, because I think that this last experiment that you are proposing is very interesting, but it's also very difficult to get observing time at the William Herschel telescope every year on a regular basis. And this is natural, because this is a very demanded telescope. It has a lot of good instruments, and I mean the oversubscription is more than 4, right? So for that, my suggestion would be to use what is called international time. I mean, we have 5%, up to 5% international time at the observatories, which would imply to use as many telescopes as you need. In this case, it would be the William Herschel and also the Isaac Newton telescope.
Okay.
This international time is meant basically for joint projects among different institutions. And these are, I mean, it's very well considered, those projects which are going to be defined to get the most from different things. An experiment to get information about the atmosphere. Okay. I mean, these projects are very well considered within this framework, and not so well considered within the normal TAC committees, because they have to evaluate the science.
Okay.
And so I would suggest you to make a good case for getting this time, and so you will be able to have possibly routine operation on those places at the observatory.
Okay, my question then is to you, can we can we ask a block, because of course if people is going to invest into equipment, they cannot wait every 6 months whether we get time or not. Can we ask like a block for X years?
If this is, I mean, this is another good thing of this scheme, is that if you are accepted, if your proposal is accepted, I mean, there are competition, there are other making proposals, right? But if yours is accepted, then you have guaranteed this time, and this can be somehow scheduled in advance, because it's clear that you need to have this scheduled in advance.
That's great.
That could
Wonderful.
be that.
So
So this is the international time, it's called.
there is a mechanism already. Of course, we have to use it.
Okay, so if there is not any other question, let's thank again Dr. Bonaccini for the talk.
Thank you very much.